So for this video, we're going to go into section 2.4 of the text, which talks about the addition of a system of coplanar forces. So once you get that text access, one thing that I wanted to point out is you'll say, oh, we skipped over section 2.3, and that is intentional. Section 2.3 is more of geometrical-based approaches to vector addition and decomposition and these sorts of things. And although they're valuable to see, particularly they will make you appreciate how easy the decomposition or linear algebra-based approaches that we are going to use in the remainder of this chapter and the remainder of the text are, it's not really worth our time to go over them because I think you will benefit much more as an engineer to spend more time on the latter course material rather than wasting an entire lecture kind of doing different examples of geometrical based approaches. But it is good to look at when you get the actual textbook and you're able to look at it. Someone should shoot me an email and let me know if you can actually see the textbook. If you remember in the intro video, I told you I could see the textbook. I just couldn't actually set up the MyLab, and still haven't heard anything back on that, by the way, but fingers crossed for tomorrow. So what is the motivation here? If you think about and you look at what's going on in 2.3, we're not fully utilizing the power that we have available to us through mathematics if we add vectors using this this geometrical approach. Instead, what we really want to do is to always try to decompose forces into vectors along some common set of axes. And the reason for that is it's going to allow us to actually transform vector addition into scalar addition. And I'll show you what that looks like in a second, and I'm sure you already know. But the key point to keep in your mind is, hey, we have this new problem as engineers. We have to add vectors, and it seems like a pain. Well, what can we do to actually break it down into something that feels a lot more like scalar addition? And in addition, we said that in the previous video, when we described this idea of decomposition, that we could really decompose a force into any two arbitrary axes we wanted, right? Because that's the way that the triangle rule works. However, if we choose to do the decomposition along orthogonal axes or axes that are at right angles to one another, what we'll find is we can rely on right triangle trigonometry in order to make the underlying mathematics easier. And if it's been a while since you've taken trigonometry, remember that right triangle trigonometry is a lot simpler. There's really only two rules that you need to remember. First and foremost is the relationship between the lengths of the side in a right triangle. Remember, a right triangle by definition has one angle, which is 90 degrees. And of course, the other two will sum to 90 since the total sum of angles must be 180. And what we know is that if we take the side length, which is opposite of that right angle, which is denoted as the hypotenuse of this right triangle, that the square of its length is equal to the sum of the squares of the other two base lengths. And this formula is known as Pythagorean's theorem. In addition, we know that there is a relationship between the angles of the right triangle and the corresponding ratios of the side lengths. Particularly if I take this angle here, A, we know that if there's some function called the sine function, such that the sine of that angle is the ratio of the length of side length A divided by the hypotenuse length C. And the way that you remember these ratios is this idea of SOHCAHTOA. Particularly, it says pick any angle, and the ratio of the opposite to the hypotenuse is the sine, the ratio of the adjacent to the hypotenuse is the cosine, and the ratio of the opposite side length to the adjacent side length is known as related to the tangent of that angle. So good practice, if it's been a little while, to go through and actually see if you can write expressions for the sine, cosine, and tangent of all of these interior angles. And hopefully it is still reviewed for you. So how do we actually do the decomposition into what's known as an orthogonal basis always? How do you actually resolve it into x and y components? Well, if we have some vector here drawn in a two-dimensional plane, remember, I can always take from its tip or the arrowhead and drop a perpendicular down. Now, I could do it either to the horizontal x-axis or the vertical y-axis, but it's just usually the way you show it, and it's easier is to drop it down to the vertical x-axis. Now notice that naturally that gives us a form of what we would call the parallelogram rule previously. This vector that is kind of forming the diagonal of this parallelogram, naturally if I were to take and view it as the sum of a vector that lied perfectly along the x-axis and a vector that lied perfectly along the y-axis, that vector that's forming the diagonal would be the sum of this vector and this vector. This vector you might recall is known as the x component. This vector is known as the y component. Now, usually, I'm using the terms a little bit interchangeably there. You usually talk about the component of the vector, not as the vector itself, but as the magnitude. But we're not going to be picky. I'm never going to ask you to write a question to differentiate the actual direct decomposition of the vector into vectors along the x and y axis or the components. Just know that basically when we drop perpendiculars from the tip to the horizontal axis, we can use right triangle trigonometry in order to write this original vector as the sum of two vectors one of which is along the x and one of which is along the y-axis. Now, question for you. That's not what we wanted. What's going on with that little I hat and j hat that they have written there? And we all remember this, but just to refresh, right? I hat and j hat are nothing more than unit vectors along the horizontal, that's the x, and the vertical, that's the y, axes. So if I have a traditional x and y coordinate system, a vector that starts at the origin and goes out 1 unit length along this horizontal axis, I just call that I hat. And one that goes 1 unit length up on the vertical axis, I will call that j hat. Now, it's okay if you are showing me any work by hand and you call this x hat. Some disciplines that is more common, particularly in the discipline that I work in, because I and j usually have some other meaning to them. But what is the beauty about having this definition of these core vectors or these basis vectors along these two axes? Well, think back to what we talked about 2 videos ago, this idea of scaling. If I have this unit vector, I can write an expression for any vector that starts at the origin and goes an arbitrary distance to the right. I just scale it by a positive k, or an arbitrary distance to the left. I just scale it by a negative k. Same idea here. If I scale j hat rather, I can make it go any distance along the vertical up and any distance along the vertical down. And from taking a combination of those 2 pairs of vectors, I can form any vector in this space. And that's why these are often called basis vectors. You can write any vector in this 2-dimensional space as a linear combination of those 2 basis vectors. Now, how are these quantities related to one another? Well, naturally, going back to our right triangle trig, we can see that the length of this vector is going to be related to, look at this notation I have here. Remember that the vertical lines are known as the magnitude of the vector times the cosine of theta. And the y component, or the length of this vector, is going to be related to the magnitude of this vector times the sine of theta. Now, again, this is where your book, sometimes I think about throwing the book away when I teach chapter 2 and just doing it by hand and only taking 20 minutes to do it. This is a much easier example to see if you don't look at it from the parallelogram point of view, but you look at it from the triangle rule point of view. If I drop my perpendicular to the horizontal axis, naturally I can write this original vector as the sum of a vector in this direction, in the horizontal, and the sum of the vector in the vertical. And if I just ignore the fact that these are vectors just for a minute, I can actually just view this as a right triangle, where the side lengths of my right triangle correspond to the magnitudes of those vectors. So this is my magnitude of my original vector, say f. Call this the vector that is along the x-axis, and this the vector that is along the y-axis. This is my x component. This is my y component. If I'm given this angle that describes the direction of that vector as a counterclockwise displacement from the horizontal axis, right, naturally, what is the sine of theta? Let's just look at this. Sine of theta. Remember, so Katoa. So the sine of theta is just going to be the ratio of the opposite the side length to the hypotenuse. What's opposite of theta? That's fy. What's the hypotenuse? That's f. So the expression that you usually see is this actually solved, which we had on the previous slide, which says that I can always compute it helps to actually do that actually in the right direction. I think if I multiply both sides by f, I can find that I can express the y component as f times the sine of theta. And you can do a similar type approach and show that the x component, which is nothing more than the length of that component along the horizontal axis, is f times the cosine of theta. So that's just how those formulas come about. They come about from right triangle trigonometry. So the question is, what if you actually had to add more than just 2 vectors together? Well, if you have to add 3, 4, or any combination of vectors in this 2-dimensional plane, and that's what they mean by coplanar vectors, you can just decompose each individually. And the key point is, once you have them into x and y components, the total resultant vector is just going to be the sum of the x components. Take that and weight the I hat vector, and the sum of the y components, take that and weight the j hat vector. And that's why when I was saying earlier, what we're really doing is we're taking vector addition, which is something that usually would follow these specific geometrical rules, and we're breaking it down into a problem that looks a lot like scalar addition, because really the components are scalars, and that's what we're adding. So how do we actually describe a resultant vector once we have it? So we've talked about how to kind of go from the resultant vector to writing it as a sum of I hat and j hat components. Of course, you know that that's called writing in rectangular form. But in addition, you can also talk about a vector written in polar form. Before I say that, one thing I wanted to mention is when a vector is decomposed into a component that is along the I hat and j hat direction, we can call that either rectangular or Cartesian form. However, when we are describing a vector in terms of its magnitude and an angle in the xy plane, traditionally, again, defined from positive x in the counterclockwise direction, that being positive, we call that a polar form description. So, of course, we can relate the polar form, again, using right triangle trigonometry. This would be a case where, so think about what's really going on here, and I'll go to the dot cam just to make it a little bit, hopefully, more intuitive. Maybe are you less intuitive? So what we had previously is what you would generally refer to as a polar to rectangular problem. Because we're assuming that we were given some information about the magnitude of a vector and its angle. So we were given mag of vector, and I'm just going to call it F, of course, because it's we're generally going to be working with force vectors, and the angle of that vector, and we want to find Fx and Fy. What we're talking about here is kind of the problem in the opposite direction. If we're given information about the rectangular decomposition, how do we find the polar form? So what that means is we're going to be given the components of the vector Fx and Fy. And remember, oftentimes we've said that you can write the vector as actually showing a linear combination like this, but another notation that we'll use often in this class is Fx and Fy put together in these kind of triangle brackets. So if I'm given that information, I know that some vector has this much on the x-axis, call that Fx, and this much on the y-axis. How do I actually go about determining the parameters of its magnitude and its direction? Well, that's just kind of like we're using the right triangle trigonometry rules in reverse, right? If I know Fy and I know Fx, well, I know the tangent of this angle, which is one of the things I want to find. So given this, we want to find mag F and theta. So I don't know what theta is directly, but I know that its tangent is the opposite side length divided by the adjacent side length. So that would just be Fy over Fx. Question is, how do I get theta by itself? Well, fortunately, there's an inverse function for the tangent. It's just known as the inverse or arctangent. If I take the inverse tangent of both sides, I can express this angle in terms of the components as the inverse tangent of the ratio of Fy over Fx. In a similar fashion, I can get the magnitude by just using Pythagorean's theorem. As we defined earlier, remember that this side length squared is going to be equal to this side length squared plus that side length squared. So let me just actually show that all written out real quick. So F squared is going to be Fx squared plus Fy squared. So this is the magnitude of the resultant vector x. So if I take the square root of both sides, what that means is I can find the magnitude of the vector, which I need to describe it in polar form, as the square root of the sum of the squares of the components. So key point is, if you know your trig, you don't ever have to actually remember those. You can kind of derive them from scratch, but we're going to be using them so much you won't have a chance to forget them, so don't worry about that part.